afternoon. This afternoon we're going to try using a video lesson so you guys can watch this video and then do some practice afterwards. My plan is to be online so that you can ask me questions either by email or possibly by Skype if that works. But this afternoon I want you to be working on the next chapter, which is about friction. And I'm going to explain a little bit about what friction is, do some examples, and then you guys can practice. And then afterwards ask me questions. So this chapter, the whole thing is all about friction. This is chapter 8. And friction has a new formula, and the formula works in combination with F equals ma and with Subat. And I'm going to show you what it's all about. I mean, I imagine you've already, got a good idea about what friction is. I sent you a video yesterday. I know that Leslie couldn't see it, but I'm going to try and put it on a different site so you can have a look at it. But friction in general is something that opposes motion. And friction makes a difference to how something is moving. So if you have an object and it's being pushed to the side, say if I was pulling it with 10 newtons going this way, then friction would be opposing motion. Friction always opposes motion, and it's worth just highlighting that all the way through, but friction would be going this way if the object is moving this way, say if it's got an acceleration of some kind. And friction always opposes motion. So if you sort of stop pulling this object that way and then started pulling it the other way, friction would flip over and it'd be on the other side. There's a really strong connection between friction and the normal reaction force. And this is partly why I've been mentioning it the whole way through. But say if this was a, 0.4 kilogram box, which means it's got a weight of 4 newtons, the normal reaction force is also the same size as the weight here, because it's not going through the floor, if that's the floor here, and it's not floating away into space, and so these two things are in balance. And it makes a difference what's going on here. So the object would be harder to move if the surface is different, and we can describe the different types of surfaces. Friction is connected to this force, and really this force is connected to this force. But we have a formula that links these two things together, because it's all about the sort of surface that the object is moving along. If it's a really slippery surface, friction is smaller. If it's a really, like a rubber surface, which is really hard to move along, this force and this force combined together would make it harder to move. The formula that connects these two things together is friction is equal to mu r, where r is the normal reaction force. That's this one, r. Friction is the one which is opposing motion, and mu is the coefficient of friction. Coefficient of friction. And the coefficient of friction describes the sort of surface this is going along. Generally, the coefficient of friction is bigger than 0. 0 would be absolutely no friction, like a smooth surface. And generally, it goes up to 1. So let's say for the majority of time, this goes up to 1. 1 would be where these two things are equal. So it takes 4 newtons to push it along this surface if mu was 1. But you do actually get values of mu which are bigger than 1, which means you have to push really, really hard. Like if it was stuck to the ground on glue, then you would have to push more than the force of the normal reaction force, the size of the normal reaction force. But generally, most of these are between 0 and 1. So you can have like a very, very small value if it was on ice. You'd have a very large value if it was on something that was hard to move along, like carpet or rubber. Just as an example, you could have different values of mu and different surfaces. So, for example, or if you had something that was really slippery, then it could be really, really small, so 0.02. That apparently is the same as skis on snow, very slippery. Or something like a smooth metal, could be something like 0.2. Or wood, is a bit bigger, a bit harder to push things along on a piece of wood if it's like a wooden floor, but still not super difficult. But if it was, you know, harder to push it along, it could be closer to 1, which apparently is a bit like rubber. So if you had a sheet of rubber and you tried to push a wooden box along it, it would be quite hard. Nowhere near as easy if it was like on a piece of wood. And you can have values which are bigger. So if you had, I don't know, something like 2, that could be something that is covered in jam, like sticky jam or sticky glue, something which is really hard to push it along. Oh, I've got a message. I'll check that later. Okay, so this is the formula we're going to use. It's the friction is equal to mu, this is the new coefficient of friction, times the normal reaction force. And sometimes you're missing this value, sometimes you're missing one of these two. But generally you're missing the frictional force to sort of combine together with other forces in a question. So if I go back to that same example I had before, if I had a box and you were pushing it to the side with 10 newtons, and it had a weight of 4 newtons, it has a normal reaction force of 4 newtons as well, because it's not floating away, it's not going through the floor, and we have a frictional force. If you're told what the coefficient of friction is, if you're told what sort of surface you're dealing with, say in this case the value of mu is equal to, let's say it's 0.3, somewhere between wood and metal, then you could say that the frictional force is equal to 0.3 times the normal reaction force, which in this case is 4. So the frictional force comes out to be 1.2 newtons. And then you could use that to work out what the acceleration is. For this one, using F equals ma, the total forces, if it's going this way, would be 10, take away 1.2, is equal to the mass, which was 0.4, times the acceleration, and then you can work out the acceleration. So that would be 10 take away 1.2, which is 8.8, divided by 0.4, comes out to be 22 meters per second. That's super fast, but it's getting faster and faster, because the frictional force isn't very big here. This is what we do. We have a situation, we've got this new force involved. Up until now we've been dealing with lots and lots of smooth surfaces, but now we have an extra frictional force. They might not tell you the size of the frictional force, but we can calculate it with this new formula. And it involves knowing the coefficient of friction. And we use mu for that. And we're going to have these where you're given mu, you need to find the friction. Sometimes you're given friction, you need to find the mu. Sometimes you're always missing one thing. After you've found everything, you might get the acceleration, and then you have to use suvat. So there's all sorts of different combinations, but it's like an extra formula that gives you extra ability to sort out these questions. Let's have a look at some more questions, because these are brilliant. Hey, this is great. I'm having a lesson where you guys don't get to answer back. No offense. I can just talk whenever I like now. But you can ask me questions, you know. Let's have a look at another one. So imagine we have something which is on a slope, right? So we could have a slope like this. I've decided to have an angle of 40 degrees, and we've got a box. And there's no forces pulling it up or down here. We're just going to have a box which is going but this box has a weight, right? The weight goes straight down towards the center of the earth. So that's 140 newtons. And then we have a normal reaction force. And we have to include this because this is essential now to our calculations. The weight is going to pull this box down the slope, and this slope has a rough surface, and the coefficient of friction is given to you. It's 0.8. Right, we can use that to work out the friction. And if this is a box on a slope and it's got a weight, it's going to pull it down, so it's going to end up moving down the slope because the weight is going to pull it down. Not the entire weight, we'll have to break that down into components, but the friction is going to go opposing motion, so the friction is going this way. All we need to do now is to work out how much of this 140 newtons is actually going down the slope. So luckily, in the same way we were doing before, this angle up here is the same as that angle, because you've got a right angle here that's 40, that must be 50. You've got a right angle here, so that's also 40. And the one that's going parallel to the slope is opposite the 40 here, so that is going to be 140 sine 40. The one that's going sort of into the slope, one that's perpendicular to the slope, that would be 140 cosine 40. Okay, and this is also important to have this one, because if we're going to work out the size of the frictional force, we use this formula. Friction is equal to mu r. Now the r is opposing this force. These two ones are the same size, because it's not going through the slope, it's not floating away into space. These two are the same size. We've got the value of mu, so that means we can work out the frictional force is 0.8 times 140 cosine 40. And then we can use a calculator to work that out. Let's have a look at the size of that. Okay, so 0.8 times 140 cosine 40, close brackets, that gives me the frictional force is 85.8. I'll be a bit more accurate because I want to be super accurate until I finish my question. So 85.79697763. Now, if I want to know what's happening, I want to know the acceleration of what this box is doing. It's going down this way, that's the positive direction. It's being pulled down by the weight. It does have some friction, but the one that's pulling it down the slope here is 140 sine 40. And I'm presuming that's bigger than the friction. Let's have a look at that. So 140 sine 40 is 89.99. So it's a little bit bigger. The one that's going the opposite direction is 85.79. The force that's pulling it down, the horizontal component parallel to the slope that's pulling it down the slope, is 89.99. So here we have F equals ma. And this is all the forces. This is just the frictional force. The one that's pulling it down the slope is 140 sine 40. Take away the friction, which is going in the opposite direction, which we know is 85.79 blah blah blah. This equals the mass, which is 14, times the acceleration. That's what we're looking for. So we're taking all the forces which are going down the slope, subtracting away the friction, which is opposing motion, and that equals ma, and then we can just do that, take away that, divided by 14, and I believe the acceleration comes out to be 0.300 meters per second squared to 3 significant figures. So what we've got here is F equals ma again. It's just that we were missing one thing, and that was the size of the frictional force, and we find that by using this new formula. F equals mu r. You have to know mu in order to find out the size of the frictional force, but you also need to know the size of the normal reaction force, and that is the same as the weight component, which is going perpendicular to the slope. Let's do another one. These are great. Okay, in my next example, I want you to imagine there is a box, and the box weighs, well, it's got a mass of 70 kilograms, which means the weight of this box is 700 newtons, and it's sitting on a surface, which is a rough surface, and the coefficient of friction is 0.15, so it's not super rough, it's just a low value, but we need to work out what's going on here. And in this particular example, we have a tension on a rope that's pulling it to the side. And this rope is being pulled at an angle of 38 degrees. So what's going to happen is we're going to have tension going that way. We're going to have friction, opposing motion. It's being pulled to the side. We just don't know the value of tension here. I want you to imagine that this is going at a steady speed. So a steady speed is another way of saying that the acceleration is 0. So everything going horizontally is actually going to balance out with everything going to the left. But we need to know the size of that friction if we're going to find out what the value of t is. This question, we're looking for the value of t. And to do this, we need to definitely acknowledge that there is a normal reaction force here. But we're also going to have a component of the tension going up the way. So there's going to be something going up from the tension. There's also going to be something going to the side of the tension. But slowly we can work out what's going on. We're going to form simultaneous equations. This is quite a big question, this one. If I break down the T into components, we end up with a different diagram. Let's have a look at that. So we've got 700 going down. We've got friction going to the left. We've got a normal reaction force, which we don't know. We've also got a tension component. This would be the one which is going straight up, which is opposite the 38. So that makes that T sine 38. We've got a force going to the right, which is T cosine 38. That's going adjacent to that 38 there, going horizontal to the surface. And we know that the acceleration is 0, and we know that mu is equal to 0.15. Let's focus on the friction to begin with. The formula for friction is equal to mu r. So friction is going to be equal to 0.15 r. Now, because the box is not flying away into space and it's not going through the table, these two together must be the same as 700. So I can say that r plus T sine 38 is equal to 700. And I can take this and I can put it where that r is. So I can form an equation which just involves T and friction, because I can do the same going horizontally. At the moment, I'm just focusing on the stuff going vertically. These are the forces which are going straight up. The r and the T sine 38 is equal to 700. So r is equal to 700 minus T sine 38. Okay, I'm just going to move this up slightly. Now, if I look at the ones going horizontally, using F equals ma, I've got T cosine 38 is equal to the friction. And the friction was equal to 0.15 r. Right? These are equal to each other because the acceleration is 0. It's really this, take away this one is 0, or just these two are in balance. The friction was 0.15 r. And r, we've already looked at, and by using the vertical components, that is equal to 700 minus T sine 38. So that's 0.15 times 700 minus T sine 38, which leaves us with an equation which is just involving T. So we can shuffle this around and find out what T is. If I multiply out the brackets and then rearrange it so all the T's are on one side, I should be able to find out what's going on. So I can say that T cosine 38 is equal to 0.15 times 700 is 105, minus this times this is 0.15 T sine 38. And if I add this whole thing to the left hand side and factorize out the value of T, I'll run out of space now. I'm just going to do this here. You end up with T, open brackets, cos 38 plus 0.15, not T, sine 38 is equal to 105, and T is equal to this divided by all of that lump, which is 119 newtons. To 3 significant figures. But it's a matter of joining these 3 different formulas together. We've got something that connects together friction and mu r. Then we've got something that is connecting together the vertical components. These two are equal to this one, and it gives us a formula which can find as an expression for r. Then we've got these two are equal to each other. It could be a motion, we could have had a bigger value of a, but using F equals ma, we can connect these two together, which is what I did here. And then I can use that going into here, and then eventually this going into where the r was, and then I can find out what's missing. There's always going to be something missing, and we can eventually find it by shuffling everything around. Let's do another one, right? Imagine you've got, this is potentially a little bit more straightforward. Imagine you've got a box on a surface. This is like a pulley question, but it's going over the side of a table, right? And you've got a box here. This is going to be 0.4 kilograms. This one is 0.7 kilograms. So we've got a weight of 4 newtons. Here we've got a weight of 7 newtons. We're going to have tension on this string, so tension here and tension here. If we say that it's released from rest, this one is going to start pulling this one down. So the motion for this object is going to be that way. This one's going to start going down. But that means we're going to have friction opposing motion here. If we're told that this is a rough surface. Let's say we have mu is equal to 0.6 and we're trying to find out what the acceleration is. What we need to do is find a value for the friction, do F equals ma on this one, do F equals a on this one, and work out what the acceleration is overall. So it's similar to the questions we've done before, it's just you have this extra frictional force which is missing. We definitely have a normal reaction force here. There's no need, this one is not on a surface, this is just sort of hanging by the string. You've got to imagine it's on a pulley here, going over the side here. There's no friction involved here, and there is no normal reaction force. You only get the normal reaction force if it's on a surface, and you only get a frictional force if it's on a surface. But whichever way it's moving, the friction goes in the opposite direction. So first of all, let's work out the size of the friction. This is more straightforward, there's nothing weird here, there's no angles involved. These two are the only two forces going vertically here, so R must be 4. And using the new formula, friction is equal to mu R, we can work out the size of the friction, which is 2.4 newtons. And then just focusing on this object, I can say that T minus friction, 2.4, is equal to the mass times the acceleration. Using this one as it's going down the way, I've got 7 minus the tension is equal to 0.7a. And really, it ends up being like a classic question that we've already done. The only difference is, to start off with, we didn't know that force, but we find it by using the coefficient of friction. Here, if I add these together, I get 7 minus 2.4, which is going to be 4.6, and 0.4 times 0.7, that's 1.1a, which makes a, just double check I got that right, 7 minus 2.4 divided by 1.1, I get an acceleration of 4.18 to 3 significant figures, meters per second squared. So we have all these things coming together now, and what I want you to do is to practice this. This takes practice, and there's a massive exercise. It's really the only exercise you need to do in chapter 8, which is all about friction. It's introducing this new thing. So we have a ridiculous amount of formulas now. We've got all the Subat ones, which are given to you. We've got F equals ma. We've now got friction is equal to mu R. And the normal reaction force is really important when you're labeling your diagrams. Don't forget about that. It's all about friction going that way, something going that way, maybe that's 10 newtons. We have a normal reaction force that's going this way, and we have a weight that's going this way. And if it's on a slope, you have to break the weight down. You have to make sure that you include the things which are going that way and going this way if it's on a slope, because that can make a difference to the normal reaction force. But try exercise 8a, which is on page 148. This is huge. It's a really big exercise, but start from the beginning, work your way all the way through. I think this will take us, a significant amount of time. See how far you can get before Thursday, and aim to try and do all of it. And as soon as you get a problem, you can email me. Just let me know which question it is you want to have a look at, and I'll work it through. And I'll try and be online during our lesson time so that you can ask me questions as the lesson progresses. Okay? Good luck.